Hey friends, Dr. Borole is here. Today we are going to continue our discussion of logic gates and combinational digital logic circuits. In that chain, we will now see how to write the Boolean equation from truth table. The procedure is simple. If the truth table is given, then first identify the entries in which Y output is 1. Then write the product term corresponds to that row for the given Y output value. Then add all the product term corresponds to Y equal to 1 as final output. That is the expression of the truth table. Now implement this expression using basic logic gates. This is the 4-step procedure. Let us see the example. Here the truth table is shown. The inputs are shown A and B and Y as output. Whereas for various combination of input from 0, 0, 0, 1, 1, 0 and 1, 1, the corresponding Y output is given in the truth table. We will identify the rows corresponds to Y output equal to 1. So row number 2 and row number 3. Right. So while writing the expression, we will consider only these two rows. The rows corresponds to Y equal to 0, that is row 1 and row 4 can be ignored. These are redundant rows. Now let us focus on row number 2 and row number 3. The mean terms for this output for row 2 is denoted as say Y1. We will see A is 0, so we will write A complement, and B is 1, therefore we write B. So this Y1 indicates that the Y output will be high when A is in the complemented form and B is as it is. Similarly, if you consider the row 3, let us say output is Y2 corresponds to this row. This Y2 is 1 when A is 1, that is already 1, and when B variable is also 1, but here B is 0, therefore we write here B complement. So when A B complement is used, Y2 will be 1, and therefore final output will be Y equal to Y1 or Y2, and therefore we will write Y is equal to A bar B or A B bar. Plus sign indicates the OR operation. Now take this expression. It consists of two inputs. We will mark the input A and B. We use two inverters to get the complemented variable A bar and B bar. Now we have four variables here, A bar and B bar. Take one AND gate for first product term. The inputs to this is A bar B. So connect A bar to one input of the AND gate and B to the another input. The output of the AND gate is A bar B. For second AND gate, we will see here the product term is A B bar. So connect A as one input. So we have connected here A as one input. And second input is B bar. So we have connected this inverter output here. So we will get the input AB bar, and therefore output of the AND gate is AB bar. So we have generated two product terms. Here Y is the OR operation of this product term. So we will take one OR gate and all the two product terms, and therefore we will get Y is equal to A bar B or AB bar. And this is same as exclusive OR operation expression, and therefore this total basic gate circuit, that is AND OR circuit, say first level is AND gate and then second level is OR gate, this logic can be replaced by a single exclusive OR gate which generates the same expression. Whereas while writing the expression from the truth table, we will now summarize again. So when the truth table is given, identify the row corresponds to the Y output equal to 1, and then write the corresponding product terms. While writing the product term, write the variable as it is when it is in logic 1 state, and use the variable complement when the variable is in logic 0 state. Then combine all the product term to get the final output. And from final output, implement the logic circuit by using AND OR logic combination. Let us see the another example. Now in this case, we will see the truth table here. In example, truth table 1 here. Y is 1 in row number 1 and row number 3. So correspondingly, the product term is, see here, A is 0, so we can use the complemented form of A. So A bar. B is also 0, so we can use B bar. So Y is equal to A bar, B bar. Now the third row, A is 1, so we use it as it is A. And B is 0, so we will write B bar. So second product term is AB bar. Whereas we have totally dropped the rows corresponds to Y equal to 0, means row 2 and row 4. So we got two product terms. We will add the two product terms. That is the ORing operation. A bar B or AB bar, and that is the expression for this truth table. You can take this expression and implement using basic logic gates. That is left to exercise for the student. See the second truth table, the another example. Here identify the row again. Row number 2 and row number 3 have Y output equal to 1. So we will consider only this row. So the product term corresponds to row number 2 is A bar B. A is 0, therefore we use A bar, and B is 1, therefore we use it as it is. The product term corresponds to now third row. When Y is 1 here, when A is as it is, say A, and when B is B bar, and therefore we write the term AB bar, and therefore the final output expression is OR operation of these two product terms A bar B and AB bar. You can take this expression and implement by using basic logic gates. Let us go to the next topic. This topic is optional, but just for the sake of additional knowledge, we will just scan through it. From the syllabus point of view, this topic is not in the scope of your syllabus. The logic expression can be represented in the digital theory by two forms. One is called as sum of product form, that is called as SOP, sum of product. And the outcome of this sum of product form can be realized by using AND OR logic network. Second form is product of sum form called POS form, and it can be realized by OR AND network. The canonical form of the Boolean expression is the form in which every product term can have all variants of the literal. Literal is the value of the variable and its complement. So for example, if you have three variables, then y output terms contains all the flavor of three variables. Means each term of y output contains all the three variables. That form is called as canonical form. We can skip this canonical form of representation because canonical form of representation is required to solve the Boolean expressions by using K-map called Carnot map for simplification. That is beyond the scope of this subject. So till the time we will go to the next topic. Let us study the universal gates. The universal gates are NAND and NOR gates. Basically, these universal gate can be implemented using three basic gates. Whereas implementation using basic gates consist of a complex circuit while fabrication. So, universal gate can implement the same function using same gate for all stages, and therefore fabrication process for digital integrated circuit will be easy, and therefore these gates are very popular because any circuit can be implemented by the use of universal gates without using basic gates. Only universal gates can be used, either NAND or NOR can be used to implement the complete circuit. Let us see the first gate, NAND gate. The name itself, it is not AND gate. The symbol of the NAND gate is already shown earlier. Now let us see how NAND gate can be used to implement a NOT gate or inverter. The inverter is nothing but y is equal to a complement or AB complement, suppose. In inverter, there is single input. Therefore, both the inputs are same. So, we can connect both the inputs to the same variable and then take the output from the NAND gate. So, you will get y here is equal to A dot B complement, where A and B inputs are same for the NAND gate, that is say A dot A complement. A dot A is A, and therefore y is equal to A complement. So you are getting the NOT gate from using NAND gate, and that is simply just connect all the inputs of the NAND gate to a single input and take the output as complement of the input. Now how to implement AND gate using NAND? The AND gate is represented by the expression y is equal to A and B. And NAND gate is NOT AND. So we will invert the NOT AND output again to get AND. So we will take double inversion here. When you can take double inversion or say double complement, the expression remains the same. Therefore, y is equal to a dot b, complement of complement is same as a dot b. Now let us see a dot b complement. This a dot b complement is nothing but a NAND gate. And the output of the NAND gate is then inverted by using the inverter. So what we do? We will connect A and B input to the NAND gate. The output of the NAND gate is A and B complement. Now here we are getting complement of the product A and B. We want to invert it. So connect a NOT gate here using NAND gate again, and therefore we connect the output here to both the inputs of the NAND gate, and we will get complement of A and B complement, and therefore double complement of A dot B is equal to A dot B itself, and therefore we can get a AND gate using NAND gate. Let us see how to implement OR gate. The OR gate is A or B, that is equal to Y. Take a double complement again. Use De Morgan's theorem here. In De Morgan's theorem, we will replace the OR operation by the AND operation and take a complement of each variable. What De Morgan's theorem says? The complement of a sum is equal to product of complement. So here A plus B complement is the complement of sum, that is equal to complement of product. Take the complement of A, take the complement of B and take a product. Okay. And the final complement will be as it is. Now therefore take the input A and B. Use the NOT gate here using NAND. So you are getting A complement, you are getting B complement at the output of second gate. Now here from the expression A complement and B complement ANDing is done. So we will use a NAND gate, A complement and B complement as input. So we will get the Y output as A complement dot B complement and complement of the total, and that is nothing but A or B. And therefore by using these combinations you will get OR gate implementation using only NAND gate. Okay, let us go to the next level. We will see the implementation of NOR gate using NAND gate. The NOR gate is represented by the expression A or B complement. Use the De Morgan's theorem. De Morgan's theorem, now replace this OR sign by product and take the complement of each, means break this complement bar individually, A bar and B bar, and take a product. And take double complement of this expression. Taking double complement doesn't affect the original expression. Now from this expression we have two inputs A and B. By using NOT gate we are getting A bar and B bar. So here you will see we get A bar and B bar. Now see the part of this expression. There is complement of A bar dot B bar. So that is nothing but a NAND operation. So connect A bar here, B bar here. So output of the NAND gate is A bar dot B bar complement. Still one complement is remaining from this expression. So use an inverter, that is NOT gate, using NAND gate and complement this subproduct. And therefore you will get here Y is equal to A complement dot B complement, complement of complement. That is nothing but A or B complement. That is a NOR gate implementation. Now let us see exclusive OR gate implementation using only NAND gate. the exclusive OR expression is given as y is equal to A exclusive OR B, and that is equal to A bar B or AB bar. Take a double complement of it, which doesn't affect the original value of the expression. Now use the De Morgan's theorem. This OR sign will be replaced by a product sign, dot. That is AND operation. Means OR operation will be converted to AND operation. And then just break a complement bar here. So we are getting A complement B complement. And in second bracket we are getting AB complement complement. The final complement bar remains as it is. Now from this expression, we can implement this expression further. You will see A complement can be achieved by using NOT gate, B variable as it is. So A complement and B is a AND operation, and the bar indicates the NOT operation of the product A complement and B, that is nothing but a NAND operation. So we will take A variable, we will take B variable. Here NOT operation can be achieved by using this NAND gate as an inverter. So output is A bar. B is connected directly to the NAND gate, second level. Then output of the NAND gate will be A complement dot B complement. Similarly, for second term, we will apply A as input to the NAND gate, and inverted value of B, that is B bar, is connected as input to the NAND gate. Then what is the output of NAND gate? Second NAND gate, A dot B complement and complement of that. And therefore you are getting the two sub term. Those terms are shown in this expression. But final complement is still remaining here. And therefore we will take this sub product and do the ANDing of this with the inversion, that is the NAND operation. And therefore final output of the final NAND gate will be y is equal to A exclusive OR B. And this way we can implement exclusive OR gate only using NAND gate. Let us see the exclusive NOR gate using NAND gate. The exclusive NOR gate expression will be y is equal to A bar B bar or AB. Now take a double inversion here and convert this expression implementable by using NAND operation. So A bar B bar complement, that is the NAND operation of the product A bar B bar. This is first complement, indicate that. The second bracket AB and there is a bar on it, means AB complement, that is nothing but a NAND operation of AB, that is AB not. Okay, and the final complement operation, that can be the inversion of these two sub term product. So take A and B again. First term implementation, we will get this AB complement. See here, AB complement. So first NAND gate gives us AB complement. Then A and B will be inverted by using these two inverters. We will get one output as A complement and second output of these inverters B complement. ANDing this, A complement dot B complement and complement of the total. We are getting the sub terms. As per the expression, we have to take the complement of the sub terms, and therefore we will have again NAND operation and generate y as output. Y is equal to therefore AB complement dot A complement B complement complement and complement of the total, that is implemented by using this expression. So we have implemented the exclusive NOR gate using 5 number of NAND gates. So if you see this table, in total, we have implemented all basic gates and extended gates only by using NAND gates. Similarly, we can implement any of the basic gates and the extended gate by using another universal gate, say NOR gate. Let us see how to implement NOT gate using NOR gate. So NOT gate is nothing but expression y is equal to a complement, and that can be easily done by connecting both the inputs of exclusive NOR gate to a single input and take the output. So short circuited input NOR gate is equivalent to NOT gate. Now AND operation, y is equal to a and b. Take a double inversion which doesn't affect the expression. Now use the De Morgan's theorem. That is the second De Morgan's theorem. Now dot will be converted to OR operation, means AND operation here shown by dot, that will be converted to OR operation, and then just separate out the complement. The De Morgan's theorem states that complement of the product is equal to sum of complements, and that is applied here. And the procedure is simple. Dot will be converted to, or this AND operation will be converted to OR operation by plus sign, and separate the variables with its complements, a complement and b complement. Now this expression can be implemented as a AND gate, y equal to ab. Now we need a complement, we need b complement. For OR operation we need one OR gate with complement, means one NOR gate. So we know how to get NOT gate using NOR gate. So we short the two inputs, apply a input here, we get a complement. Here also same thing, short the two input of second NOR gate, apply b input, you will get b complement as output. Now here in the NOR gate, two inputs are there, a complement and b complement. So if you read it NOR gate as OR NOT, so first make a OR operation, a complement or b complement, and this final bubble is a complement or NOT operation. So a complement or b complement and complement of it. So we are getting the y expression as y is equal to a complement or b complement complement, and that is nothing but a dot b, we have shown here on the left hand side. Now OR gate implementation using NOR gate. The name itself indicate the NOR gate is not OR. So if you take a NOT operation at the output of a NOR gate, you are getting the original OR gate. So if you have y is equal to a or b to be generated, then just generate NOR operation of a or b and then take a inversion. So here a is input, b is input to a NOR gate. So output of the first NOR gate is a or b complement, and then take another complement by using NOT gate. NOT gate is just simply connect the two inputs of the NOR gate to the output of first NOR gate. The final output will be then a or b complement of complement, and that is nothing but a or b, that is OR gate output. So here we have implemented OR gate using two NOR gate. First NOR gate generates the NOR operation and second gate generates the NOT operation. So NOR NOT gets the OR. Now third gate implementation using NOR gate is a NAND gate. NAND is A and B NOT, that is nothing but NAND. Use the De Morgan's theorem, separate out, convert product to the sum. of complements. So A complement or B complement is Y. That is using De Morgan's theorem. Take a double complement of it. That will give you A dot B complement. That is a NAND output. So here take this sub expression. We need A complement as one variable. Another variable is B complement. And then you will see here there is a NOR operation of the A complement and B complement. And then there is a complement operation of the output of this NOR gate. So first we need A complement and B complement. So we use the NOT gate using NOR gate. A and B as input here to two NOR gates. We are getting A bar and B bar as output. Take a NOR output from these two, that is A bar or B bar complement. That is the output of this second level of NOR gate. Here we want additional complement, isn't it, from this expression. We got the partial answer here. So we have take the complement of this sub output by using another NOT operation. And therefore we got the final expression Y is equal to A complement or B complement and complement of it. That is nothing but A dot B complement. And that is nothing but A dot B complement is nothing but a NAND of A and B. And this way NAND gate can be implemented using NOR gate. Similarly, exclusive OR gate can be implemented using NOR gate is shown here. The output Y is equal to A bar B or AB bar. That is nothing but the exclusive OR gate output expression. Take a double complement. Use the De Morgan's theorem now to convert the OR operation to the product operation or AND operation. Separate out the complements here in the first step. Then again apply the De Morgan's theorem to the bracket term. We are getting, again convert this AND operation to OR operation and break the complement bar here into, so A complement of complement or B complement. So you are getting A complement of complement is A or B complement. Dot is as it is. Now again here De Morgan's theorem apply to this second term. You are getting A complement or B complement of complement. Complement of complement is the same variable, so B. So A complement or B, and the final complement operation is as it is. Now we have the variables here A, B bar, A complement, B bar. So we generate the complement variable using two NOT gates here using NOR gate. Then take the variable and combine A and B bar by using the NOR gate operation. That is A or B bar NOT. Now second NOR gate A bar or B NOT. That is the output of second NOR gate. Combine this by using the NOR operation. And then take an inversion. Actually we want to have a OR operation here, isn't it? So therefore these two gates is equivalent to a OR gate. So first this third level of the gate gives you the NOR operation and invert it. So you will get OR operation, and therefore this term and this term will be ORed here. See here, this term and this term with OR operation. And therefore Y is equal to A exclusive OR B is generated. Let us see the example. Draw the logic diagram for De Morgan's theorem using only NOR gates. The first De Morgan's theorem, that is basically a NAND operation. De Morgan's first theorem is a NAND operation. The product of the complement is equal to sum of complements. Now A complement and B complement is required here. Take A and B. This is a NOT gate using NOR gate. So A complement here you will getting at the output of first NOR gate. B complement will be available at the output of second NOR gate. Take a NOR operation of it. You are getting A complement or B complement complement. But we want just A complement or B complement. So we can revert the inversion operation by using additional NOT operation using the NOT gate using NOR gate. And therefore you are getting the output A complement or B complement. So equivalently, if you see this, the NAND gate is equivalent to inverted input OR gate. De Morgan's second theorem, it's the reverse one. The complement of the sum is equal to product of complements. So what this is doing here? The OR operation is now converted to AND operation. So plus sign is changed to dot sign. And this over bar, that is the complement bar, that will be break in two parts, A bar and B bar. So therefore the statement complement of a sum is equal to product of individual complements. So first take the complement of A and B. Here see, A is connected to an inverter using NOR gate, you get A complement. B is connected to the inverter again using NOR gate, you are getting B complement at the output. Take a NOR operation, you are getting A complement or B complement of complement. But we are interested in A complement and B complement. But where you are getting here is additional complement operation. So take a NOT operation of it. So we are getting this expression, A complement or B complement double complement. And using De Morgan's theorem, you will convert it to A dot B complement, and that is nothing but a NAND gate. And therefore this way the second De Morgan's theorem can be implemented by using 4 number of NOR gates. So we will stop here today. In the next lecture we will see various logic circuit building blocks used in digital electronics. Till then, bye bye friends.